Hello everyone, welcome back to RC Circuits. This is lecture number 4. So in previous lecture we have discussed an RC circuit with the input as a square wave input. Uh, so in this square wave input we are assuming the frequency is very low. So we are applying very low frequency of square wave input. Low in the sense we are giving enough time for the circuit to reach to steady state at any point of the DC value. So if you are at 10 volt, we are maintaining the 10 volt as much as time such that the circuit has reached to steady state, and even for minus 10 volt also, and since the duty cycle is 50%. So now we will look at the same circuit, but this time we are not giving enough time for the circuit to reach to steady state. It means the time period of the circuit, or the half of the time period, which means the duration of the 10 volt or the duration of the minus 10 volt is such that uh, the circuit has not reached to its steady state value. So uh, we can draw the input waveform. So let's say this is the input waveform. So plus 10 volt, minus 10 volt, and we will draw the voltage across the capacitor. So uh, in last question, in last problem, the capacitor has reached to its complete input voltage, but this time, since the time period t by 2 is very low, this time period I am assuming this is very low compared to the time constant of the circuit, or the 5 time constants of the circuit. So that means it is not reaching to 10 volt, so it may reach to some other value, right? So for simplicity we can assume this half of the time period t by 2 is time constant of the circuit, which means if you wait for this time, half of the time period, then the voltage across the capacitor has reached to 63.2% of its final value, because the initial voltage we are assuming as 0. So it will reach from 0 to 6.32 volt. Then from here, now the input voltage is changed to minus 10 volt. So in that case, this is the input voltage, and we have the capacitor and resistor. Now for this circuit, the initial voltage of this circuit is 6.32 volt, and it may reach to some other steady state value if you wait for another half of the time period. So it may go to, I don't know, maybe some, I'm assuming it will go to some negative value. That depends on the time constant of the circuit. So if you write the expression of this graph, then if you leave the circuit, then it will go to minus 10 volt. So this final value is minus 10. So final value plus initial value minus final value times e power minus t by tau is equal to this waveform, right? So what is this value? This value you will get when you put the t value as this time, right? So this time is nothing but t by 2. So t by 2 is nothing but the time constant of the circuit that we have assumed. So I'm saying if you wait for one time constant, then you will get this value, which is nothing but minus 10 plus 6.32 16.32 e to the power minus 1. So you understand this, right? This expression is this one, and if you put the t value in place of t, if you put this duration, then you will get uh, the value at that point of time, so which is nothing but this one. So let's calculate that. E power minus 1 times 16.32 minus 10 is minus 3.99. So I am assuming it is approximately equal to minus 4 volt. So let's say it is reached to minus 4 volt. Now again, will it reach to 6.32 volt again? Definitely not, because it will reach to 6.32 if the initial voltage is 0. But here the initial voltage is minus 4 volt, right? So at this point, the input voltage is changed to 10 volt, and we have capacitor and we have resistor, and the capacitor starts charging in this direction now. Previously it was charged in this direction. Now the initial voltage of the capacitor is minus 4 volt. So this is in this direction. Now the capacitor starts charging in this direction, and this minus 4 become plus 0, and then again starts increasing to positive value. So let's say it charged to some voltage, we don't know. So let's find out that. For this circuit, the final value is 10 volt, right? So final value plus initial value is minus 4. Final value plus initial value minus final value times e power minus 1. I am writing directly e power minus 1 because to get the voltage at this point. So at this point, if I want to get the voltage, then I have to take this much duration. The duration is same as tau. So you will get so e power minus 1 is 0.367 times 14. So which is 4.84 volt. So definitely it cannot reach to 6.32. It will reach to less than 6.32. So we got 4.84 volt. And now again, if it was at 6.32, it has reached to minus 4 volt. Now the initial value is reduced, so it will reach to some more magnitude, right? So definitely it will be more than minus 4 volt. So I am not calculating this now. So from logic we can say this will be more than the magnitude of 4 volt, or you can say it is less than minus 4 volt. And again this will charge to some voltage. So if you see here, initially it was 0, then 6.32, then minus 4, then 4.84, then some other, let's say minus 5, we don't know. So this keeps on changing, right? So how can we decide? So at steady state, let's assume it has reached to some constant oscillations. So let's say this is Vc of t, and this is Vn of t. So at steady state, now forget about some initial graphs. So at steady state, from negative to some positive voltage exponentially increasing, and again it is discharging to again the same voltage. So let's say this is Vy and this is Vx. So from Vy to Vx, then from Vy to Vx it starts charging up, and then it is charging in negative direction. It is not discharging, it is charging in negative direction. That's it. So this is what is happening at steady state. Now how can we find this Vx and Vy? Let's see. So this is Vc of t, and we can also draw, in separate graph V0 of t. I am saying V0 is output across the resistor. So V0 of t is at steady state so here I'm assuming the input voltage is minus 10 volt, right? That's why it starts discharging towards minus 10 and it reached to Vy. So at this point, at input value of minus 10 volt, what is the output voltage? So for input of minus 10 volt and the capacitor is charged to Vy, actually the capacitor will charge in this direction. If it is charging in this direction, I have to get this polarity, right? But forget about the polarity. I am just taking Vy as absolute value. It means if Vy is negative, then I will get plus minus, let's say minus 6 volt. It means it is charged to 6 volt in this direction. That's why I have taken the polarity of a plus minus and absolute value of Vy. So this is Vy, and we have a resistor. So here V0 is minus 10 minus Vy. Here Vy is negative, then you will get more than minus 10, right? So let's say it is here. So at this point I have minus 10 plus Vy, and then immediately the capacitor starts charging. It means the input voltage should have been changed to plus 10 volt. So from here to here the input voltage is suddenly changed to 10 volt, but the voltage across the capacitor at the same time should remain constant, right? So it should be plus Vy only. So this is Vy and we have resistor. So the input voltage is changing, but the voltage across the capacitor remains constant. So this should change, right? So now V0 is 10 minus Vy. So here Vy is negative, so you will get more than 10 volt. So immediately after the input voltage is changed to plus 10 volt, then output voltage across the capacitor will go from minus 10 plus Vy to plus 10 minus Vy. Minus 10 minus Vy to plus 10 minus Vy. So I'm assuming this is plus 10 volt and this is minus 10 volt. So this should be inside this minus 10 and this should be above this plus 10. And then the capacitor voltage starts increasing, and since the input is constant at plus 10 and this starts increasing from Vy to Vx, so this value starts increasing, then this node voltage is V in minus V cap, right? Capacitor voltage. So since this is increasing, this node voltage starts decreasing. So you will see this kind of exponential decay. So at this point, input voltage is 10 volt and the capacitor is charged to Vx, then the output voltage is changed to from this point to 10 minus Vx. So from here to here, the capacitor is charged to plus Vx. So the output voltage is now 10 minus Vx. That is what I have written here. This is 10 minus Vx. This one was 10 minus Vy, right? Now again from here, so it was charged to Vx and then immediately the input voltage is changed to minus 10. That's why the capacitor starts going towards negative value. So from here to here again the input voltage is changed to minus 10 volt. But since the capacitor does not allow the sudden change, the capacitor voltage should be at plus Vx. Then we will get V out as minus 10 minus Vx. Here Vx is also positive. So you will get the value which is below minus 10 volt. So it will go to here. This value is minus 10 minus Vx. So what is the magnitude of the that okay, will come later. And again from here to here, so the capacitor voltage starts moving from Vx to Vy in negative direction, right? It was at Vx and it moved to Vy. So the input voltage is minus 10 volt and the capacitor value starts moving from Vx to Vy. Here Vy is negative. Don't think that it is charging in positive direction. It is still charging in this direction only, but Vy is negative. So in this case V0 is minus 10 minus Vy. So it will again charge to this value at this point. This value is same as minus 10 minus Vy. And again the same theory. It will go to again 10 minus Vy. Then this will exponentially decay. And then this will go here. The same theory. This will keep on continuing. So this is the steady state graph or steady state waveform of output voltage across resistor, and this is the steady state waveform of voltage across capacitor. So if you see here, what is this magnitude? This is 10 minus Vy minus of minus 10 minus Vy, which is nothing but 20 volt. And here also if you see, 10 minus Vx minus of minus 10 minus Vx, which is nothing but 20 volt. So what is this 20 volt? This magnitude is same as that of this magnitude, right? So it means whatever the change in the input voltage is happening, it is happening from minus 10 to plus 10. The same magnitude of change is also happening at the output voltage, because the capacitor value should remain constant even though the even though the change in the input, irrespective of change in the input. So that is what it is doing. And yeah, so how can we find this values? So it is charged to plus Vx and it is charged to minus Vy, or it is charged to Vy in negative polarity and it is charged to Vx. How can we find that? So here the input voltage was minus 10 and here the input voltage should be plus 10, then only it will start charging towards positive direction, right? So if you write the expression for this waveform, then what is the final value? Final value should be plus 10 volt. It should not be Vx, it should be plus 10 volt. So final value plus initial value is still Vy. So initial value minus final value times e power minus t by tau. That is this expression. Now the capacitor starts charging towards minus 10. So the final value should be minus 10. Final value plus initial value is still Vx. Initial value minus final value times e power minus t by tau. So that is this expression. Now this this duration is one time constant, right? So if you substitute in place of t the duration of this time, which is nothing but one time constant, which is RC. So this is half of the time period. We assumed that half of the time period is RC. So if you do that, then you will get this value. This value is nothing but Vx, right? So I am saying write that. So Vc1 is final value plus initial value minus final value e power minus t by tau, and Vc2 is final value plus initial value minus final value e power minus t by tau. So at t is equal to t by 2, which is nothing but one time constant, which is RC, then Vc1 should be Vx. It is going from Vy, which is initial value, to Vx at this point, and at the same time then Vc2 should go to Vy, right? So if you do that in place of Vc1, if you write Vx, I mean if you want to write in place of Vc1 to write Vx, then you should put t as tau, which is nothing but e power minus 1. So Vx is 10 plus Vy minus 10 e power minus 1, and if you put tau here, then you will get Vy. So Vy is minus 10 plus Vx plus 10 e power minus 1. So how can you find Vx and Vy? You have two expressions and two unknowns, so you can easily find Vx and Vy. So if you add these two equations, then you will get Vx plus Vy is Vy e power minus 1 minus 10 e power minus 1 plus Vx e power minus 1 plus 10 e power minus 1. This and this are cancelled. So Vx plus Vy is equal to Vx plus Vy times e power minus 1, which is possible only if Vx plus Vy is equal to 0, which means Vx is equal to minus Vy. So from the math we are good. I mean, we got Vx is equal to minus Vy. But even before, if you look at the input voltage, and if you look at the circuit, input voltage is changing from plus 10 volt to minus 10 volt, which is symmetrical change, right? I mean, so uh, and this is expected, so it should charge to some voltage, and the capacitor should discharge to the negative voltage of same magnitude, because the voltage magnitude is same even in negative polarity. That's why we are getting plus Vx and uh, minus Vy. I mean, these magnitudes are same. If it is charged to some 4 volt, then it should have charged to minus 4 volt in negative direction. That is what from math also we got the same. And if you want to get the Vx and Vy values, then substitute in any one of the equation. Let's do that. So I am substituting in 1. So Vx is equal to 10 plus minus Vx minus 10 e power minus 1. So if you find this one, you can calculate this one. Minus 1. So I'm getting 4.62 volt. So it is charging to 4.62 and it is discharging to minus 4.62. So this is how you will get the output across the capacitor at steady state. So forget about the initial condition, I mean initial waveform. So you will get, so it will charge from minus 4.62. This is it, iteration. So starting we have solved, right? So this one, and so it keeps on charging and discharging, and once if it gets close to this one, so once if it is charged to minus 4.62, then this will be in repetition. This will again charge to 4.62 and charge it to minus 4.62. So this is the Vc of t waveform, and you can also draw the output voltage waveform across the resistor. So this is how the circuit will behave if the time constant is very high compared to the duration of the input voltage. So yeah, if you want, you can also try doing by taking even higher time constant. Here we have taken this duration is nothing but one time constant, right? So you can try with the duration is even lower. It is half of the one time constant. So you can try that and try to get the steady state waveform. Yeah, that is what about that circuit. And let's solve some more circuits for first order, and this is a good example of, you will get some circuit analysis also. So here we have dependent current source, and yeah, we will try to solve this circuit. So, and this is again, it is again a simple circuit. You can try to solve this one. So let's try first solving this one. So at t is equal to 0, the switch is opening. So here assume, we will keep this circuit aside. So in this circuit, the switch is opening at t is equal to 0. So assume the circuit has reached to steady state for t less than 0, or the switch was closed for long time for t less than 0. So assume like that. Then for t less than 0, the circuit looks like the switch was closed, right? It is 100 volt and it is 2 ohm. And we have a dependent current source. This diamond or this box indicates the dependent source. Here, since it is showing the symbol as current, so it is a current source, and this can be dependent on either the voltage across any component or it can be current also. I'm saying the value. So this value here I, it is depending on the current flowing through the 3 ohm resistor. It can be the voltage across this 3 ohm resistor also. So the dependent source value can be either voltage or current, but the source is either current source or voltage source is depending upon this symbol. So this is for t less than 0. So now assume the circuit has reached to steady state, right? It means the capacitor has fully charged. It means it is open circuited. So there is no current flow here. Now what is this steady state voltage across this capacitor? We will try to find that. So this is Vc of infinity. This infinity I am saying the steady state for t less than 0. So if you know about nodal analysis, then it is simple. So here I have Vc of infinity, right? Even without nodal analysis, you can solve this one. So if this is Vc of infinity, this node voltage, the node voltage is nothing but the voltage at this point with respect to any reference in the circuit. So I am taking the reference as this node. So since this is reference, then this node voltage is nothing but Vc of infinity, and this node voltage is 100 volt. If this is 100 and this Vc of infinity, then current flowing through this 2 ohm resistor is the potential difference across two nodes divided by this resistor value, right? So here the current flowing is 100 minus Vc of infinity by 2, and at the same node we have I by 2 current flowing in this direction and I current flowing in this direction, right? So this is I by 2 and this is I, which means this should be I by 2, right? So since this current is 0, the 100 minus Vc of infinity by 2, that current should come here. So then this value should be equal to this I by 2, right? You understand? So this I by 2 should be equal to 100 minus Vc of infinity by 2. Then 100 minus Vc of infinity is equal to I. This is one equation. And what can be other equation? So since this is Vc of infinity, I mean to find Vc of infinity, we have two unknowns here. So we have to get one more equation uh, in terms of Vc of infinity and the current I. Since this is Vc of infinity and these two are same nodes, and this is also should be Vc of infinity, and this current is I, right? So since this current is I, then the node voltage is, the series resistor is 4 ohm. So the drop across this resistor is 4 ohm times the current I. So it is just a resistor of 4 ohms with respect to this node. I will get the drop as 4 times I. So this is the voltage. This 4 times I is nothing but Vc of infinity. So Vc of infinity is 4I. We don't want I, so we will just find Vc of infinity. So if you substitute I here, Vc of infinity is 4 times 100 minus, yeah, so this is 4 times 100 minus Vc of infinity. Then if you solve this one, you will get, so you will get 80 volt. So Vc of infinity is 80 volt. It means let me have the waveform for t less than 0 also. So we are applying input voltage as 100 volt. So this is V in. Then the voltage across the capacitor goes to from 0 to 80 volt exponentially at steady state. So it will charge to 80 volt, then it stays at 80 volt. So this is Vc of t. Let's say this is minus t1. Here I am taking this t1 just to write the expression of this voltage waveform. So assume this 100 volt has been applied at t is equal to minus t1, which is way before t less than 0. That is what I am trying to show here. So yeah, this is fine. But if you want to find this time constant, if this is minus t1, then this will reach to steady state in 5 time constants, right? So this should be from here to here, this should be 5 time constant. So this is minus t1 plus 5 tau1. So how can we find tau1? Since it is a first order RC circuit, then tau1 is nothing but R equivalent times C equivalent, right? So if you look at this circuit, this is a first order RC circuit and we have only one capacitor here. So C equivalent is nothing but 1 by 32 farad. And what is R equivalent? R equivalent is we are finding time constant at t less than 0. So at t less than 0 we have this 100 volt. So if you have 100 volt, this should be short circuited to find the resistance between these two terminals, which is capacitor terminals. So if you do that, if you short circuit the input voltage, then So for R equivalent at t less than 0. So short circuit the input voltage, and we have some resistor here which is 2 ohms I think, and then uh, we have dependent current source of I by 2, then we have a resistor. I am just combining those two resistors, it is 4 ohm, and we have current flowing through that resistor is I, and this is dependent current source, and this is 2 ohm. Okay, yeah. Now see here the capacitor terminals is between these two terminals, so we have to find the R equivalent between these two terminals. So let's say this is R1, and let's say looking between these two terminals right side is R2. So between these two terminals we have 2 ohm resistor is connected, and between these two terminals let's assume uh, this is a black box, and if you find you will get some equivalent resistance of R2. So between the same two terminals we have R2 also. So what is the R equivalent? If you have two resistors between two terminals, it should be in parallel. So R equivalent is nothing but R1 parallel R2. R1 we know it is 2 ohm. Now it is just we have to find R2. So forget about this left side R1. Now you have to find only this right side equivalent resistance. How will you find that? So we have I by 2, 4 ohms, I. Now general what we have to do at this type of circuits, here you cannot open circuit this current source, because this is not independent current source, this is dependent current source. You cannot open circuit this one, because if you want to open circuit then I by 2 should be 0. If I by 2 is 0, then here current flowing is 0, so it has no meaning here. So you should keep the dependent source, you should only make 0 only independent sources. So if this is there, then in general we have to find this equivalent resistance by applying a test voltage, or you can also apply a test current source. So here I am applying test voltage source, and if you find the current through this test voltage source, then R equivalent is nothing but, so looking from here you will get Vt by It, right? So if you do Vt by It, then you will get R equivalent, I mean R2 in our assumption. So that is one way. Also, if you pump some test current source, let's say this is It, then if you find the voltage between the current source, across the current source, then if you find Vt by It, then you will get R equivalent. So here R equivalent is Vt by It, right? So assume if It is equal to 1 amp, if you pump 1 amp current source, then directly we will get R equivalent as Vt. So what I am saying is, better you pump 1 amp current source and find the voltage across that current source, which is Vt. Then if you find Vt in this expression, you will directly get the value R2. So this is node voltage is Vt. So here the drop is 4 times I. So Vt is nothing but 4I. This is one value, and see 1 amp is coming here and I by 2 is coming here, then combinedly it is going to this 4 ohm. So 1 plus I by 2. So 1 plus I by 2 is the current flowing through this 4 ohm, which is nothing but I, which is given. So I by 2 is 1 amp, so I is also 1. Then Vt is 4. If you substitute here, then you will get Vt is 4. Sorry, I is 2. So this is 8. So R2 is 8 ohms. So the right side equivalent resistor is 8 ohms and left side is 2 ohms, and these two are in parallel, right? So R equivalent is 8 into 2 by 10, which is 1.6 ohms. So what is tau 1 is C equivalent times R equivalent. 16 by 10 is the R equivalent, and what is C? 1 by 32. So you will get 1 by 20 seconds. So if you wait for 50 milliseconds or 0.05 seconds, then from here to here, then the 5 times of this 50 milliseconds, then you will get the capacitor voltage as 80 volt approximately, and it will stay at 80 volt, and it is open circuited and current flowing through that capacitor is 0. That is fine. Now this is only for t less than 0. Now at t is equal to 0, the switch is getting opened. It means there is no independent source in this circuit, right? For t greater than 0 at all. It means the capacitor will fully discharge to 0. So we will find the values later, but from 80 to definitely it will go to 0. That is for sure, because there is no independent source in the circuit for t greater than 0. So this will go to 0 exponentially, and this will stay at 0. So this will happen at 5 tau 2, and this is 0. That's it. The graph we got very early. It will charge from 0 to 80 volt, and from 80 volt it will discharge. But to find the time constant, you have to do some circuit analysis. So we can also do that. So for time constant for t greater than 0. Now what is the circuit for t greater than 0? It is only this capacitor and this part of the circuit. So if you want to find R equivalent, then we don't have R1 now, right? So this we don't have, only the right side we have. So right side we already found, which is 8 ohms. So for tau 2 we have only right side, which is t greater than 0. So tau 2 is R2 times C equivalent. So C equivalent is 1 by 32, I think. Forgetting this one. And R2 is 8 ohms, which is 1 by 4. So if you wait for 0.25 seconds or 250 milliseconds, which is more than the tau 1, right? So then it will go to how much? 36.6% of its initial value, which is 80 volt. So let's say this is tau 2, then this value should be 0.367 times 80 volt. You calculate that later. So that is what it is happening in this circuit. So I just wanted to show this circuit to uh, do some circuit analysis. What will happen when you have both the dependent sources and independent sources? And yeah, so you can also write the expression of the circuit. So this is Vc of t, you can write that one. So if you remember, so this expression is, final value is 80, right? So 80 into 1 minus e power minus t by tau 1, that is fine. But we have this graph, right? So it means this is left shifted by t1. It means we have to replace the t with t plus t1. So replace t by t plus t1 to get this graph. So Vc of t is 80 times, by the way, this is 80 times 1 minus e power minus t by tau 1 u of t. This is only for t greater than 0. So if you replace that, then minus t plus t1 by tau 1 u of t plus t1, and also we have this graph, right? So this is 80 e power minus t by tau 2 u of t. So this is only for t greater than 0, and this is only from minus t1 to 0. Yeah, that is how this circuit will work. And we can solve one more circuit. This is simple compared to the previous one. This is not mentioned. Okay, let's take it for at t is equal to 0, the switch is closed. We can directly draw the output waveform V0 of t. The voltage is staying continuously at 50 volt. So even at t less than 0 it is 50, and even at t greater than 0 it is 50. Previous circuit we don't have the independent source for t greater than 0, right? But here we have at t less than 0 the same voltage, and at t greater than 0 also we have the same independent voltage. So will the capacitor stays at same value, or will it go to a different value at t is equal to 0 or for t greater than 0? That we can discuss now. So we have completely 50 volt across all time. So this is V in of t, and if you want to draw V0 of t, then so for t less than 0, see the switch is closed at t is equal to 0. Before that the switch is open. It means you have 3 ohms also, 3 ohms, 1 ohm and capacitor. So you can draw for t less than 0, 50, 2 ohms, 3 ohm, 1 ohm and cap. So at steady state this will be open circuited. So this current is 0. So you will get, since this current is 0, this is Vc of infinity, this drop is 0, this is also Vc of infinity. So Vc of infinity is 50 times, this is 3, and I am applying voltage division rule, 3 by 5, which is nothing but 30 volts. So at some point, let's say we are applying here, and it will reach to 30 volt. It will reach to 30 volt and it stays at 30 volt. This is for t less than 0. So what is the time constant? You short circuit this voltage source, then you will get these two are in parallel, which is 2 ohms and 3 ohms, and which is in series with 1 ohm, right? You are looking from here. This is R equivalent. So R equivalent is, if you short circuit, then I am writing directly 2 and 3 are parallel. So which is 6 by 5, which is 1.2. 1.2 plus it is in series with 1 ohm. So 2.2 ohms. So the tau 1 is 2.2 times 1, which is 2.2 seconds. So from here to here 5 times 2.2 seconds to reach to steady state. And now the initial voltage is at 30 volt. Now the transient behavior is happening at t is equal to 0. So at this time there is short circuit across 3 ohms, right? So for t greater than 0 you have the same input voltage, but there is short circuit across 3 ohms, and you have this and this. See what will happen to this circuit. Since there is short circuit, whatever the current coming from the input source will directly go through this short circuit. It will not go through this branch, right? So this is 0 amps. This will completely go to the short circuit path. So since it is 0 amps, since it is 0 amps, there is no uh, voltage build up across the capacitor further. This will be open circuited. There is no charge building further in the capacitor, so it will stay at the same voltage. So even there is independent voltage source, since there is a short circuit path across this one, this will be invalid. All the current will go through that short circuit path and the capacitor voltage will stay at 30 volt only. So if you want to write the expression, so this one is 30 times 1 minus e power minus t by tau, right? So if you left shift this one by t1 units, let's say this is minus t1, then you replace this with t with t plus t1. So you will get dc of t is 30 times 1 minus e power minus t plus t1 by tau 1 u of t plus t1. Yeah, that is the expression. So this is how the circuit will behave. We will solve more complex circuits in coming lectures. So if you have any doubts, you can comment down. If you like this video, you can share with your friends. Thank you.